Okay, just take a look around you for a second. I'm willing to bet you can see concrete somewhere. It's in our buildings, our bridges, our sidewalks. I mean, it is literally the foundation of our entire modern world. But this ancient material has a pretty serious hidden flaw. So today we're going to dive into the state-of-the-art concretes that are stronger, smarter, and way greener than anything the Romans could have even dreamed of.
But first, let's talk about the problem. Here's a number I really want you to remember: 8%. The production of Portland cement, that's the key ingredient in concrete, is responsible for a staggering 8% of all global CO2 emissions. To put that in perspective, that's more than the entire aviation industry. So yeah, the very material we use to build our world is also one of the biggest reasons it's warming up.
So this brings us to a huge question, right? We can't just stop using concrete. That's not an option. So can we reinvent it? Can we make it stronger, more durable? And this is the big one, can we make it sustainable? Well, the researchers we're looking at today believe the answer is a huge, resounding yes.
So welcome to the world of state-of-the-art concrete. And look, this isn't just one material. Think of it more like a whole family of advanced compounds where each one is specifically engineered to solve a particular problem and just push the boundaries of what we thought was possible in construction.
All right, let's kick things off with the most obvious upgrade, raw power. The first group of materials we're going to check out are all about achieving just incredible strength and durability, making our structures tougher and longer lasting than ever before.
At the very top of the pyramid, you've got ultra-high-performance concrete, or UHPC. You can basically think of this as the absolute pinnacle of concrete technology right now. And it's not just about strength. It's got this super dense microstructure and fiber reinforcement that gives it unbelievable durability. It even has the ability to hold itself together after it cracks. Wild, right?
Now check this out, because the scale of this improvement is just massive. The standard concrete in your sidewalk or in a building foundation, that might have a compressive strength of around, say, 30 to 40 megapascals. UHP? It can get all the way up to 200 megapascals. That is not a small step up. It's a giant leap. It lets us do things like build impossibly thin bridges or skyscrapers that use way less bulky material.
So, you might be wondering, how is that even possible? Well, it's all about some brilliant material science. First, engineers use extremely little water, which is usually a weak point in regular concrete. Then they optimize the mix with particles of all different sizes, so there are basically no empty voids left. It's like a perfect 3D puzzle. Then they add tiny steel or synthetic fibers to hold it all together. And sometimes they even cure it with heat and pressure. Every single piece is fine-tuned for just maximum performance.
Now, building on that whole idea of fiber reinforcement, we have a cousin to UHPC, fiber reinforced concrete, or FRC. With this one, the main goal isn't just about peak strength. It's about changing how the concrete behaves when it fails. You see, those little short scattered fibers act like a web, holding the material together even after a crack starts. This is what keeps a tiny crack from turning into a catastrophic failure.
Okay, so where is this actually useful? Well, think about anywhere you need a material that can bend instead of just snapping. Regular concrete is brittle. It just breaks. This stuff is way more ductile. It bends first. This makes it absolutely perfect for things like earthquake-resistant buildings, industrial floors that take a constant beating, and for lining tunnels. FRC gives these structures the toughness they need to be safer and much more resilient.
Strength is one thing, but what if you could actually change the construction process itself? This next category of superconcretes is all about flow, making it way easier to build really complex, intricate designs that were, once nearly impossible.
I want you to meet self-compacting concrete. The name really says it all. This stuff is so flowable, it pours like a thick syrup, filling every single nook and cranny of a complex mold or weaving around dense steel rebar all on its own. You don't need any of that noisy, labor-intensive mechanical vibration to get the air bubbles out. It just does the work for you.
But how do you control something that acts like a liquid but hardens like a solid? Well, through some really rigorous testing. Engineers use things like the slump flow test to see how far it spreads, the V-funnel to check its viscosity, and the L-box to make sure it can pass through tight spaces. So it's not just a wet mix, it's a precisely engineered material.
And if you take this idea of flow to its absolute logical conclusion, you get 3D printed concrete. By squeezing out a carefully designed concrete mix layer by layer, we can build these incredible geometric shapes without any molds or formwork at all. And this quote just captures it perfectly. It's about unlocking a whole new level of architectural freedom.
And now for the biggest challenge of them all, sustainability. Because look, all the strength and flowability in the world doesn't really matter if our main building material is harming the planet. This next type of concrete is designed specifically to tackle that massive carbon footprint.
Remember this number. That 8% from Portland cement production is the problem we have to solve. The super energy-intensive process of creating what's called cement clinker is the main culprit. So to make concrete green, you have to attack the problem right at its chemical source.
And here it is, a truly radical solution: geopolymer concrete. This is a fundamental change in chemistry. Instead of using Portland cement, GPC uses industrial waste products, like fly ash from coal plants, and activates them with an alkaline solution to create a powerful binder. It completely sidesteps the traditional carbon-heavy process.
So what's the bottom line? Geopolymer concrete can slash the carbon footprint of concrete by around 50%. And when we're talking about an industry responsible for 8% of all global emissions, a 50% cut isn't just an improvement, it is a potential game changer.
And you know what the best part is? It's not a compromise. Geopolymer concrete is a seriously high-performance material all on its own. It literally takes industrial waste and turns it into something incredibly valuable. It's often more durable and more resistant to chemicals and fire than regular concrete, and it hits impressive compressive strengths that are perfect for most construction jobs.
So, we've got concrete that's ultra-strong, self-placing, and dramatically greener. I mean, the future of construction looks pretty bright. But if these materials are so revolutionary, why aren't they everywhere yet?
Yeah, there is still some real-world hurdles to get over. For one, these advanced materials can be more expensive. And crucially, the standardized building codes and design guides that engineers have to follow haven't really caught up to the technology yet, and that slows down adoption. And of course, scaling up the production of these specialized components to a global scale is a huge logistical challenge.
But here's the thing, these are challenges of adoption, not of fundamental science. The potential is absolutely there. We are right on the verge of reinventing this ancient material. So I'll just leave you with this to think about. Our entire world as we know it was shaped by the limitations of conventional concrete. What kind of world are we going to build when those limits are gone?